Gravity holds the entire universe together, yet we still do not know what it truly is. What if this familiar force is not a force at all, but a stream of invisible particles? This is the Gravitron hypothesis, the revolutionary idea that gravity is carried by a fundamental particle. We are embarking on a journey to the edge of known physics to see if this particle truly exists. By the end, you will understand how confirming the gravitron could completely reshape our world, from floating cities to travel among the stars. We will explore why this particle has remained hidden and what its discovery would mean for our future. What invisible force most captivates your imagination? Every single one of us feels gravity's constant pull, a force so ordinary we rarely give it a second thought. An apple falls from a tree, and we do not question the invisible hand that guides it down. Our entire world is built upon this predictable tug, from the way we walk to the orbits of planets around the sun. Yet, this most familiar of forces is also the universe's greatest enigma. We have mastered the other fundamental forces. Electromagnetism, for instance, is beautifully explained. We know it is carried by particles of light called photons, which act as messengers for the force. We can manipulate it to power our cities and send information across the globe. But gravity stands apart, a stubborn outlier in our otherwise elegant map of the cosmos. This is the central conflict, a deep crack in the foundation of physics itself. Albert Einstein revealed that gravity is not a force in the traditional sense, but rather the warping of the very fabric of space and time. A massive object like the Sun creates a dip in this cosmic fabric, and the Earth simply follows the curve like a marble rolling around a bowl. This theory of general relativity is breathtakingly accurate. Yet, in the bizarre world of the ultra-small, governed by quantum mechanics, every force must have a carrier particle. So where is gravity's particle? This is the profound puzzle that has confounded physicists for generations. We have two incredibly successful theories, each proven correct in its own domain, but they present completely different pictures of how gravity works. They cannot both be the final story. This is the void, the missing piece that the gravitron hypothesis attempts to fill. Could this elusive particle be the messenger that bridges Einstein's curved spacetime with the quantum realm? Our understanding of the universe's fundamental forces is codified in a powerful framework known as the Standard Model. This is the rulebook for the subatomic world, a stunningly accurate map of nature's smallest building blocks and the forces that govern their interactions. It tells us that 3 of the 4 fundamental forces are communicated by specific messenger particles. For the electromagnetic force, the carrier is the photon, the particle of light that brings us sunshine and carries our radio signals. Then there is the strong nuclear force, the incredibly powerful glue that holds the nuclei of atoms together, and its messengers are aptly named gluons. Finally, the weak nuclear force, responsible for processes like radioactive decay, is carried by the W and Z bosons. This system is a masterpiece of predictive power. We can smash particles together in giant accelerators and watch as these messengers are created and detected, exactly as the model foretells. Yet, this elegant picture has one monumental, undeniable gap. Gravity is completely absent from the party. The force that shapes the cosmos on the grandest scales, that sculpts galaxies and guides planets, has no assigned particle in our most complete theory of the small. This glaring omission is the single greatest unsolved problem in physics. It is as if we have written a perfect symphony but are missing the deep, foundational bass note that holds the entire composition together. This silence is what makes the search for the graviton so compelling. We are hunting for the one particle that could finally make the universe's score complete. Why has this fundamental piece of our reality remained so stubbornly hidden from view? This missing particle, the hypothetical graviton, emerges from a profound mathematical necessity. To fit within the quantum framework that so perfectly describes every other force, gravity must have its own messenger. The graviton is not conceived as a tiny ball of matter, but as a ripple, a discrete bundle of vibration in the fabric of spacetime itself. Its theoretical properties are incredibly specific and strange. It must be massless like the photon, allowing it to travel at the speed of light and extend gravity's influence across the vast emptiness of space. It must have no electric charge, for gravity affects everything equally, regardless of whether it is positive or negative. Most distinctively, it is predicted to be a spin-2 particle. Think of spin not as literal rotation, but as an intrinsic angular momentum that defines how a particle behaves. A spin of 2 means the graviton would interact with matter in a unique way, perfectly mirroring the geometry of Einstein's curved spacetime. This is not a random guess. When physicists take the equations of general relativity and translate them into the language of quantum field theory, the mathematics itself demands the existence of this exact type of particle. The numbers simply do not work without it. This theoretical convergence is why the search is so compelling. We are not hunting for just any particle. We are looking for the one specific entity that the deepest laws of physics insist must be there. Finding the graviton would do more than just fill a gap in a chart. It would be the final, crucial stitch that weaves together the universe of the very large with the universe of the very small. It is the essential key to a theory of everything, a single, coherent set of rules that describes every interaction from the birth of a star to the dance of quarks. Without the graviton, our understanding of reality remains fundamentally incomplete, a beautiful tapestry with one central thread still missing. This popular name, the Gravitron, hums with a different kind of energy than the clinical term graviton. It sounds less like a fundamental particle and more like a machine, a device you could power up and control. Science fiction has long embraced this vision, painting pictures of gravity drives on starships and personal devices that cancel weight with the flick of a switch. The name itself suggests a future where gravity is not just a force we endure, but a tool we wield. This shift in language is crucial because it transforms the search from a purely theoretical pursuit into a tangible quest for a new technological age. Confirming the graviton's existence would be the first step toward engineering the gravitron. Imagine the implications. Our entire relationship with the physical world would be rewritten. Construction would be revolutionized with massive structures assembled effortlessly in zero-gravity fields. Transportation could become a matter of gliding above the ground, free from friction and fuel. The energy required to leave Earth's grasp, currently a monumental challenge involving enormous rockets, could be drastically reduced. The gravitron hypothesis is so compelling not just because it completes a chart of particles, but because it promises a key. It is the key to a box containing technologies that sound like magic to us today. This potential is what fuels the immense challenge of the hunt. How do you detect a particle so incredibly feeble that it barely interacts with anything at all? The search for the graviton is the central quest in one of science's greatest challenges, the problem of quantum gravity. Our two most powerful descriptions of reality, general relativity and quantum mechanics, speak entirely different languages. One describes a smooth, curved fabric of spacetime, while the other depicts a frenetic, probabilistic world of quantized energy. For decades, physicists have struggled to find a common tongue, a single theory that can reconcile the cosmic with the subatomic. This is the grand unification challenge, and at its heart lies the graviton. The core of the problem is gravity's profound weakness. On the scale of atoms and particles, the gravitational force is so vanishingly small it becomes utterly insignificant. To see its quantum effects, you would need to concentrate an immense amount of energy into a point smaller than a single proton. The forces required are far beyond anything our most powerful particle colliders can ever hope to achieve. It is like trying to hear a single whisper in a roaring hurricane. This incredible feebleness is why gravity's quantum signature, the graviton, has remained completely hidden from our experiments. Yet the human mind refuses to accept this impasse. Several brilliant paths have been forged in an attempt to bridge this divide, and they all point toward the graviton. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. The different vibrations of these strings give rise to all the particles we know, from electrons to photons. Crucially, one specific vibration pattern perfectly matches the predicted properties of the graviton. In this framework, the graviton emerges naturally as a closed loop of string, a tiny vibrating thread of spacetime itself. Another profound approach is loop quantum gravity, which reimagines spacetime not as a smooth continuum, but as a fabric woven from minuscule, discrete loops. Here, the graviton is thought to be an excitation of this fabric, a tiny ripple traveling across the network of loops. Both theories are mathematically breathtaking, but they are also incredibly complex, pushing the very limits of human comprehension. The equations involved are so difficult that finding exact solutions can feel like trying to map a mountain range in complete darkness. This is not just a technical problem, it is a conceptual Everest. We are trying to describe the rules for the very stage upon which the universe plays out, and the tools we have seemed to break down the moment we look too closely. The graviton is the ghost in this machine, the key that could finally unlock the door to a unified theory of everything. This profound weakness makes the graviton the ultimate ghost in the machine. Catching one is a challenge that pushes the very limits of what we consider possible. The reason lies in the minuscule strength of gravity itself. Compared to the electromagnetic force, gravity is weaker by a factor of 1 with 40 zeros after it. To put that almost unimaginable number into perspective, the gravitational pull between two electrons is trillions upon trillions of times weaker than their electromagnetic repulsion. This means a graviton, the messenger of this feeble force, would almost always pass through any detector without leaving a trace. It would ignore solid matter as if it were not even there. To have any realistic chance of observing a single graviton, we would need a detector of almost absurd proportions. Some calculations suggest a machine the size of Jupiter, made of a perfectly sensitive material, and even then, you might have to wait for the age of the universe just to register one signal. The energy required to create a graviton is similarly astronomical, far beyond what the most powerful particle colliders can produce. Our current technology is like trying to feel a single snowflake land on your shoulder during a blizzard, with your entire body encased in armor. This is why no graviton has ever been seen, and why some in the scientific community view the direct search as a futile, almost philosophical pursuit. They argue we are chasing a phantom, a mathematical artifact that can never be empirically confirmed. Yet this immense difficulty does not deter the most determined minds. If we cannot catch a single graviton, perhaps we can listen for the chorus. Yet the silence is not absolute. We are not completely blind in this search. A monumental breakthrough has given us a new way to listen to the cosmos, providing the most compelling indirect evidence for the graviton's reality. This evidence comes not from catching a single particle, but from observing the grand chorus of them in action. In 2015, the LIGO Observatory made history by directly detecting gravitational waves for the first time. These are the ripples in spacetime that Einstein predicted a century ago, generated by cataclysmic events like the collision of two black holes. When such an event occurs, it sends a shudder through the very fabric of the universe, a wave that stretches and compresses space itself as it travels outward at the speed of light. Think of a still pond on a calm day. If you toss a single pebble into the center, you will see a series of tiny, expanding ripples. Now, imagine that pebble is an object with the mass of 30 suns, and the pond is the structure of reality itself. The resulting wave is what LIGO measured. From a quantum perspective, what is a gravitational wave if not a vast collection of gravitons? Just as a beam of light is composed of innumerable individual photons, a gravitational wave can be thought of as a coherent stream of countless gravitons all moving in sync. Each detection of a gravitational wave is in essence a detection of gravitons en masse. We are not seeing the individual snowflakes, but we are most definitely feeling the blizzard. This is the strongest circumstantial case for the graviton's existence. The properties of these waves match exactly what a quantum theory of gravity would predict. They travel at the speed of light, they are massless, and their behavior aligns with the theoretical spin-2 nature of the graviton. Every time our instruments register another cosmic shudder from a neutron-star merger or a black hole collision, we are gathering more evidence that we are on the right path. We are hearing the universe whisper the graviton's name over and over again. But where do we look for this ghostly particle on Earth? Our most powerful tools for such a hunt are particle accelerators, colossal machines like the Large Hadron Collider. These rings of immense power are designed to smash protons together at velocities approaching the speed of light, recreating the fiery conditions of the early universe. The hope is that in this momentary, cataclysmic release of energy, something entirely new and exotic could blink into existence, including perhaps a graviton. The theoretical pathways for its creation are as fascinating as they are complex. One leading idea involves the concept of extraspatial dimensions beyond the three we experience. In this mind-bending scenario, gravity appears weak to us because it is diluted, spreading out into these hidden dimensions. Inside a particle collision, however, the incredible concentration of energy could allow a graviton to be created and then immediately vanish, escaping into these other dimensions. From our perspective in the three-dimensional world, the telltale sign would be a single, dramatic burst of missing energy. We would see all the energy and momentum going into the collision, but not all of it coming out. It would simply vanish, carried away by an invisible fugitive. Another possibility is that the collision energy itself becomes so immense that it directly ripples space-time, producing a graviton that stays within our dimensions. Experiments at the LHC have scoured the debris of countless trillions of collisions, searching meticulously for this exact signature. They have looked for events where energy disappears without a trace, or for subtle distortions that could hint at a graviton's brief passage. So far, the result is a profound silence. No definitive signal has ever been found. This silence, however, is not a failure. Every null result pushes the possible mass or energy scale of the graviton to ever higher values, telling us where it cannot be. It is like searching for a lost city, and with every empty valley we cross, we narrow down the map, guiding our search toward more distant and exotic mountain ranges. The hunt continues, forcing us to ask if our machines are simply not yet powerful enough, or if the graviton is hiding in a corner of reality we have not even begun to fathom. The emptiness of our particle colliders does not mean the hunt is over. It simply means we must look elsewhere, to a laboratory of unparalleled scale, the universe itself. To find evidence for the graviton, we need to peer back in time to the very first moments after the Big Bang. In that initial, incomprehensibly hot and dense state, the four fundamental forces were likely unified into a single, primal superforce. As the universe expanded and cooled, these forces separated one by one. The moment gravity broke free is a pivotal event we can still observe the echoes of today. This is the story written in the oldest light in the cosmos, the cosmic microwave background. This faint afterglow, a snapshot of the universe when it was just 380,000 years old, is our most powerful window into this primordial era. It reveals a universe of stunning uniformity, but with tiny, crucial variations in temperature. These tiny ripples are the seeds from which all cosmic structure would grow, every galaxy, star, and planet. But what planted these seeds? The leading theory points to a period of hyper-accelerated expansion called inflation. a fraction of a second after the universe began. During inflation, the vacuum of space itself was seething with quantum fluctuations. On the smallest scales, pairs of virtual particles, including gravitons, would constantly blink in and out of existence. As the universe inflated at a rate faster than light, these microscopic quantum jitters were stretched to astronomical sizes. The gravitational pull of these fluctuations, mediated by gravitons, imprinted themselves onto the fabric of spacetime, creating the density variations we see in the cosmic microwave background. In this view, the entire large-scale structure of the cosmos is a fossilized imprint of primordial quantum gravity, a direct consequence of gravitons at work. Yet, there is an even more subtle clue hidden in this ancient light, a signature that could be the smoking gun for the graviton. This clue lies not in the temperature of the cosmic microwave background, but in its polarization. As this first light traveled through the early universe, it interacted with the primordial soup of particles and the fabric of spacetime itself. Think of light as a wave that can vibrate in particular directions. The gravitational tugs from those first inflationary ripples would have twisted this light, leaving a distinct curled pattern in its polarization known as B modes. This specific swirl is the unique fingerprint of primordial gravitational waves, the very waves that a chorus of gravitons would create. Detecting this signal is one of the most intense pursuits in modern cosmology. It would be a direct glimpse into the quantum nature of gravity operating at the very birth of the universe. It would tell us that gravitons were not just present, but that they were actively sculpting the cosmos in its first fleeting instance. Finding this pattern would be like discovering the original architectural blueprint for our universe, a blueprint drawn by the hand of quantum gravity itself. This persistent silence in our search for the graviton forces a profound question. What if we are looking for something that simply is not there? A growing chorus of physicists proposes a radical alternative, suggesting that gravity is not a fundamental force to be quantized at all. This is not a fringe idea, but a serious attempt to solve the same puzzle from a completely different angle. One of the most prominent challenges comes from a theory known as modified Newtonian dynamics, or MN. Its core premise is startlingly simple. Perhaps our understanding of gravity's behavior is incomplete, not its underlying nature. MN suggests that at extremely low accelerations, like those found in the far outskirts of galaxies, the force of gravity behaves differently than Newton or Einstein predicted. This single tweak to the equations can remarkably explain the rotation of galaxies without needing to invoke the presence of dark matter. For decades, astronomers have observed that stars at the edges of galaxies orbit far too quickly. According to known gravity, these galaxies should fly apart. The prevailing solution has been to propose that invisible, unseen dark matter provides the extra gravitational glue. MN offers a different fix, suggesting the glue is not missing matter, but a modified law of gravity itself. If MN is correct, the need for a graviton particle vanishes, because gravity would operate under different, non-quantum rules on cosmic scales. Another deeply fascinating idea is that of emergent gravity. In this view, gravity is not a fundamental force like electromagnetism. Instead, it emerges from the collective behavior of countless microscopic degrees of freedom, much like temperature emerges from the frantic motion of atoms. You do not look for a temperature particle in a gas, because temperature is a statistical property of the whole system. Proponents of emergent gravity argue that space-time and its curvature are similarly illusions, macroscopic consequences of a deeper, underlying quantum reality we do not yet perceive. Gravity, in this picture, is a thermodynamic force, an entropic push that arises from a natural tendency toward disorder. It would be as real as the pressure in a steam engine, but just as derivative. These theories are compelling because they address glaring cosmic puzzles, yet they face their own monumental challenges. MN, while successful with galaxy rotations, struggles to explain the behavior of massive galaxy clusters without some form of dark matter. Its integration with the full framework of general relativity remains an open and difficult problem. Emergent gravity, for all its conceptual elegance, is still in its early mathematical stages, lacking the precise predictive power of more established frameworks. So why does the majority of the physics community still hold fast to the graviton hypothesis? The answer lies in a principle of unparalleled success: unification. Every time in history we have probed deeper into nature, we have found that forces are transmitted by particles. Electromagnetism, the weak force, the strong force, all were unified under the quantum umbrella. Gravity is the last holdout. To abandon the quest for its quantum carrier would be to accept that gravity is a permanent exception, a cosmic anomaly that operates by a completely different set of rules than every other interaction in the universe. It would mean our universe is fundamentally less unified and less elegant than we believe it to be. The graviton represents the final piece of a puzzle we have been solving for a century. Giving up on it feels to many like giving up on a fundamental truth about reality itself. The choice is stark: a universe where gravity is a unique geometric force, or one where it finally joins the quantum dance with its own messenger particle. Our daily reality is one of heavy, grounded objects, but science fiction offers a world of weightless wonder. The idea of a gravity particle has long escaped the confines of physics journals to become a staple of our collective imagination. In countless stories, this hypothetical particle is not a ghost to be hunted, but a tool to be mastered. Spaceships are equipped with gravity drives that bend spacetime for faster than light travel, allowing crews to cross galactic distances in the blink of an eye. Characters wield personal gravity projectors, leaping between skyscrapers or pinning adversaries to the floor with an invisible force. These narratives transform the graviton from an abstract concept into the Gravitron, a powerful piece of technology that defines entire futures. This cultural adoption does more than just entertain. It shapes how the public perceives the very real scientific pursuit. When we watch a film where a hero manipulates gravity to avert a disaster, or play a game where solving a puzzle involves reversing a room's gravitational field, we are not just passive observers. We are being subtly educated. These stories introduce the core idea that gravity might be a force we can understand and ultimately control. They frame the search for the graviton not as an obscure academic exercise, but as a quest for a key that could unlock humanity's potential. This connection is powerful. A teenager enthralled by a science fiction novel might be inspired to study physics, driven by the dream of one day turning that fiction into fact. The fictional Gravitron sets a cultural and technological target, a vision of what could be possible if we finally decode the universe's most stubborn secret. It fuels a sense of wonder that, in turn, drives real-world support and interest in the complex, often opaque, research happening in laboratories and observatories around the globe. The stories we tell about controlling gravity are, in essence, rehearsals for a future we are actively trying to build. The ability to cancel gravity would rewrite the laws of our physical world. Imagine a cityscape where vehicles glide silently above the ground, not on wheels or tracks, but on a cushion of manipulated spacetime. This is the promise of true anti-gravity, a technology that would emerge from our mastery of the graviton. If we could produce and control a field of gravitons, we could theoretically create a local region where gravity's pull is neutralized or even reversed. Transportation would be the first and most dramatic revolution. Personal cars and mass transit pods could float effortlessly, eliminating friction with the ground. This would mean travel at incredible speeds with minimal energy expenditure, transforming our cities into multi-layered networks of silent, efficient movement. The familiar roar of engines and the screech of tires would be replaced by a near-total hush. This is far beyond even the most advanced magnetic levitation systems we have today. Maglev trains still require a track and powerful electromagnets to push against it. An anti-gravity system, by contrast, would push against the fabric of space itself, requiring no physical contact and freeing vehicles from any predefined path. The very concept of a road would become obsolete. Construction and architecture would undergo an equally profound transformation. Building a skyscraper currently involves an immense struggle against gravity, with cranes lifting massive steel beams against a constant downward pull. With gravity control, that fundamental struggle disappears. Enormous structural components could be maneuvered into place as if they were weightless. We could assemble entire sections of a building on the ground and then gently lift them to their final position. This would not only make construction faster and safer, but it would allow for designs that are currently impossible. Architects could create sprawling, floating platforms, delicate latticeworks that defy conventional support, or entire districts built in the air, connected by bridges that are beautiful, slender threads rather than heavy, load-bearing structures. The city of the future would not just be built on the land, it would be woven into the sky, a testament to our final victory over the force that has anchored us for all of human history. The freedom to move beyond our atmosphere would become as simple as steering a car. A propulsion system based on the Gravitron would not push against anything in the conventional sense. Instead, it would manipulate the geometry of spacetime around a spacecraft, creating a wave for the ship to ride. This is the principle behind theoretical concepts like the Alcubierre warp drive. Imagine the spacecraft sitting inside a bubble of flat spacetime. The drive would compress the fabric of the universe ahead of the bubble while expanding it behind. In this scenario, the ship itself does not move through space faster than light, a violation of Einstein's rules. Instead, the space around it moves, carrying the bubble along like a surfer on an ocean wave. The vessel rests motionless inside this warp bubble, protected from the immense tidal forces and debris that would otherwise obliterate it at such velocities. The light speed barrier remains unbroken, yet it is gracefully circumvented. A journey to Alpha Centauri, which would take tens of thousands of years with today's rocketry, could be reduced to a matter of weeks. This is not mere science fiction, but a direct application of the equations of general relativity, solutions that remain impossible without a deep understanding of the quantum particles, the gravitons, that would mediate such a profound curvature of reality. For more local travel within our own solar system, the concept of gravity surfing becomes feasible. A ship could generate a localized gravity well in front of it, effectively falling continuously toward its own creation. It would surf the gravitational slope it makes, accelerating without expelling propellant. The journey to Mars would no longer be a 9-month ordeal dictated by orbital mechanics and fuel constraints, but a swift, direct glide lasting perhaps a few days. The entire solar system transforms from a distant, hostile void into an accessible neighborhood. Moons of Jupiter and Saturn, with their subsurface oceans and unique chemistries, become viable destinations for exploration and even colonization. The dream of becoming an interplanetary species hinges on overcoming the tyrannical cost of escaping gravity and crossing the void. Mastering the Gravitron offers the key to that lock, turning the solar system into a backyard and the stars into destinations on a map. The very air around us is alive with invisible signals, a chattering web of radio waves and microwaves that connects our modern world. Yet this entire electromagnetic symphony has fundamental limits. Radio signals cannot penetrate deep water or the heart of a planet, and they weaken dramatically over interstellar distances, dissolving into the background noise of the cosmos. A new form of communication could bypass these limitations entirely, using the fabric of reality as its medium. This is the promise of gravitational wave communication, a technology built on the mastery of gravitons. Imagine a device capable of emitting a controlled, patterned stream of these particles, creating gentle, coherent ripples in spacetime itself. Unlike light or radio waves, these ripples would be virtually unimpeded by any form of matter. A gravitational signal could pass directly through the Earth, through a star, or through an entire galaxy as if they were not even there. There would be no need for satellite relays or complex networks of undersea cables. A message could be sent from one side of the planet to the other in a perfectly straight line, right through the planet's molten core, emerging on the other side with its information perfectly intact. This would create the most resilient and direct communication network imaginable, one that is immune to solar flares, atmospheric interference, or any form of physical obstruction. For deep space exploration, this technology would be nothing short of revolutionary. Our current methods of talking to distant probes, like the Voyager spacecraft, rely on giant radio antennae and involve communication delays of many hours. A gravitational communication system would offer a clearer, more direct channel. A probe orbiting a moon of Saturn could send its data back to Earth not as a faint radio whisper that must be carefully extracted from cosmic static, but as a clean, unambiguous tremor in spacetime. More importantly, the nature of this communication could offer unparalleled security. An electromagnetic signal can be intercepted by anyone with a receiver in its path of travel. But a gravitational signal, because it interacts so weakly with matter, would be almost impossible to eavesdrop upon. You could not simply tap a cable or point a dish to listen in. To detect the signal, you would need to be virtually at the exact location of the sender or the intended receiver, placing your detector directly in the path of the spacetime ripple. This inherent property makes it the ultimate secure channel, perfect for military, governmental, or any sensitive data transmission across vast distances. This system would not merely be an upgrade to our current technology, it would be a complete paradigm shift, a successor to the electromagnetic age. We have built our modern world on the back of the photon, but its reign may one day end. The Gravitron could take its place as the primary messenger of our civilization. Picture a future where the internet is not a web of radio waves and fiber optics, but a constant, subtle hum of manipulated gravity. A conversation happening not through the air, but through the bedrock of the universe. This network would be silent, invisible, and omnipresent, connecting humanity across continents and, eventually, across star systems with a fidelity and security we can barely conceive of today. The shift from electromagnetic to gravitational communication would be as profound as the leap from messenger pigeons to the internet, marking the moment we truly learn to speak the language of spacetime itself. Your own personal gravity field could become as adjustable as the temperature in your home. This is not about massive starships or global communication networks, but about the intimate, daily revolution of personal gravity control. Imagine a sleek wristband or a subtle implant that communicates directly with the fabric of spacetime around you, creating a localized bubble where gravity's pull is a setting you control. With a simple mental command or a gesture, you could dial the effective gravity down to a fraction of Earth's normal or increase it to multiples of its strength. The implications for health and fitness are staggering. Rehabilitation from injuries would be transformed. A patient recovering from a broken leg or spinal surgery could begin their physiotherapy in a low-gravity environment, practicing movements and rebuilding muscle without straining healing bones or joints. As they grow stronger, the gravity level could be gradually increased, providing a perfectly calibrated resistance that matches their recovery progress. For athletes, this technology opens up entirely new frontiers of training. A boxer could train in high gravity, throwing punches against immense resistance to build explosive power, then switch to low gravity to practice complex combinations with enhanced speed and agility. A basketball player could perfect their jump shot while floating effortlessly, focusing purely on form before returning to normal gravity with newfound precision. But the applications extend far beyond the clinic and the gym. Your home itself could become a dynamic environment, a room might have zones with different gravity settings. Your workspace could be set to a gentle, lunar-like pull to reduce physical fatigue during long hours at a desk. Your bedroom might maintain a slightly lower gravity to ease the strain on your body for a more restful sleep. For pure entertainment, the possibilities are limitless. A children's playroom could become an indoor zero-gravity playground where they can tumble, flip, and float to their heart's content. Your backyard could host a party where guests gracefully leap over fences and float between conversations. Sports would be completely reinvented. We could see the emergence of entirely new athletic disciplines played in variable gravity arenas. A game similar to soccer might be played where players can jump 20 feet into the air to head a ball, requiring a whole new understanding of trajectory and teamwork. Or consider a form of three-dimensional chess where players navigate and manipulate pieces in a weightless cube. This level of control over our most fundamental physical experience would fundamentally alter our relationship with our own bodies and our environment. It promises a world where physical limitations are not fixed, but are instead parameters we can adjust for our well-being, our performance, and our sheer enjoyment. The force that has defined human movement since the dawn of time could become the ultimate personal accessory. The same force that anchors us to the planet could one day power our entire civilization. This vision moves beyond controlling gravity for movement and into the realm of harvesting it for energy. The principle is familiar on a small scale. A hydroelectric dam uses the gravitational potential energy of water high in a mountain reservoir. As the water falls, its energy is captured by turbines. Now, envision a technology that taps directly into the gravitational field itself, without needing a waterfall or any moving parts at all. This would be the ultimate power source, a generator with no fuel, no emissions, and no waste. The entire Earth is a massive gravitational well, and a device that could siphon even a minuscule fraction of that constant, relentless energy would provide limitless electricity. One theoretical device is a gravitational potential energy converter. Picture a loop of superconducting wire, cooled to near absolute zero, positioned vertically within the planet's gravitational field. According to quantum mechanics, a magnetic flux through such a loop is quantized, meaning it can only exist in specific, discrete levels. As a virtual particle-antiparticle pair, including virtual gravitons, spontaneously forms and annihilates within the field, the tiny gravitational interaction could, in theory, induce a change in this magnetic flux. This would generate a persistent electrical current in the loop, effectively converting the ambient gravitational energy of the Earth directly into usable power. It would be like placing a water wheel not in a river, but in the very fabric of space, catching the endless, subtle drizzle of quantum gravitational events. The energy source would be the planet itself, a battery that never depletes. The scale of this potential is almost incomprehensible. A network of such converters could be deployed anywhere from the bottom of the ocean to the heart of a desert, providing base load power to the entire globe without a single smokestack or solar panel. The concept extends beyond our world. An advanced civilization might build massive energy collectors around more powerful gravitational sources, like neutron stars or even black holes. These cosmic engines would harness the immense spacetime curvature, the ultimate expression of gravitational power. While this remains a speculative leap, it underscores a profound truth. Unlocking the quantum secret of gravity does not just mean new machines, it means accessing the fundamental energy of the cosmos. The universe is not just held together by gravity, it may one day be powered by it. But the graviton's reach may extend far beyond the force we feel. It could be the key to illuminating the universe's greatest shadow, dark matter. This mysterious substance outweighs all the visible stars and galaxies by a factor of 5 to 1, yet it refuses to interact with light. We only know it's there because of its immense gravitational pull, which holds spinning galaxies together and bends the path of light itself. For decades, its true nature has been a ghost in the cosmic machine. What if dark matter is not completely isolated? What if it experiences its own forces, a hidden physics operating in a parallel cosmic realm? This is where the Gravitron story takes a fascinating twist. Some physicists propose that dark matter particles don't just feel gravity, they also interact with each other through their own version of a fundamental force. And just as the photon carries the electromagnetic force for our world, this dark force would need its own messenger particle, a dark graviton. Think of our universe as having a hidden parallel layer. In our visible sector, standard gravitons mediate the gravity we know. In the dark sector, dark gravitons would facilitate interactions between dark matter particles, creating complex structures like dark atoms or even dark stars, all completely invisible to our telescopes. This idea elegantly solves several puzzles. It explains why dark matter seems to clump in ways that simple, non-interacting models struggle to account for. More importantly, it forges a profound link between our search for the graviton and the hunt for dark matter. They may not be two separate mysteries, but two sides of the same cosmic coin. The discovery of our universe's standard graviton would be the first step into this hidden world. By confirming that gravity is quantized in our sector, we would have powerful evidence that the same principle must apply in the dark sector, making the existence of a dark graviton almost inevitable. It would give us a theoretical blueprint, a set of rules to guide our experiments. We would know what kind of signatures to look for in particle colliders or sensitive underground detectors. Finding the standard graviton would not just complete our model of the universe, it would hand us a map to the 85% of it that has been missing. One discovery could unlock two of cosmology's deepest secrets, revealing a universe far more complex and interconnected than we ever dreamed. These brilliant theories, however, run headfirst into a mathematical wall. The central problem is known as non-renormalizability. In simple terms, when physicists try to apply the standard quantum rules to gravity, the equations explode. They produce infinities that are impossible to remove. For the other three forces, we have a mathematical toolkit, a process called renormalization, that neatly sweeps these infinities under the rug, allowing for finite, sensible predictions. But with gravity, this toolkit fails completely. The infinities multiply uncontrollably, rendering the calculations useless. It is as if you are trying to balance your checkbook, but every time you add a column of numbers, the result is an infinite sum of money. The math simply breaks down, suggesting that our current quantum framework is fundamentally incompatible with Einstein's theory of gravity on its own terms. This is not a minor technicality, it is a screaming alarm that our understanding is incomplete. This mathematical breakdown forces theorists into speculative territory, like the extra dimensions proposed by string theory. Yet these ideas create their own profound challenges. How do you test for a dimension that is curled up into a space a billion times smaller than an atom? Our most powerful particle colliders probe incredibly tiny scales, but they are still far, far too large to directly detect these hypothetical dimensions. The evidence would have to be indirect, like the missing energy signature from a graviton escaping our reality. But such a signal could also be explained by other, more conventional particles like neutrinos, which are also notoriously difficult to detect. This leads to a fundamental question of falsifiability. If a theory is so flexible that it can explain any possible outcome, or if its key predictions are forever beyond our experimental reach, does it still qualify as science? Or does it drift into the realm of philosophy? This brings us to the deepest conceptual rift of all. Can a force described as pure geometry, the very curvature of the universe, truly have a discrete particle-like counterpart? Einstein's general relativity paints a picture of a smooth, continuous fabric. The quantum world is defined by jerkiness and packets of energy. Marrying these two visions feels like trying to describe a flowing river as a collection of individual frozen droplets. The graviton, in this view, might be a useful mathematical fiction, a way for our quantum-based minds to approximate a geometric truth that is ultimately continuous. Perhaps we are forcing gravity into a quantum box when it was never meant to fit. The path to the gravitron is not a straight line, it is a maze of unsolved puzzles. Each proposed solution opens up new, more difficult questions, pushing the frontiers of both mathematics and philosophy. The very definition of reality hangs in the balance. This global quest unfolds across a breathtaking range of scales, from the cosmic to the microscopic. In space, a revolutionary observatory is taking shape. The Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart. They will use lasers to measure the distance between them with unprecedented precision, listening for the low-frequency gravitational waves that ground-based detectors cannot hear. These are the ripples from the most colossal events in the universe, the mergers of supermassive black holes at the hearts of galaxies. LISA will open a new window onto the gravitational universe, hearing the deep bass notes of the cosmic symphony. Back on Earth, the next generation of ground-based observatories is poised to amplify our hearing even further. Projects like the Einstein telescope in Europe and Cosmic Explorer in the United States are designed to be vastly more sensitive than current instruments. They will be built deep underground to shield them from seismic noise, allowing them to detect gravitational waves from the very edge of the observable universe, perhaps even from the first moments after the Big Bang. At the opposite end of the spectrum, tabletop experiments are searching for the faintest whispers of quantum gravity. These are not massive machines, but exquisitely sensitive setups involving supercooled mirrors and tiny, levitated spheres. They aim to measure whether gravity itself has a quantum nature by seeing if a massive object can be placed in a quantum superposition, being in 2 places at once under its own gravitational pull. The results could provide the first direct laboratory evidence for the graviton's reality. What unites these vastly different endeavors is a spirit of profound international collaboration. The search for the graviton knows no borders. Scientists from competing nations and institutions are pooling their intellect, resources, and data, working toward a common goal that transcends politics. This is humanity united in an effort to answer one of its most fundamental questions, a testament to our shared curiosity about the universe we call home. The quiet hum of a supercooled experiment might be the first place we hear it. New generations of quantum sensors are pushing the boundaries of the measurable, turning what was once theoretical noise into a potential signal. These devices operate at temperatures colder than the void between galaxies, using quantum tricks to isolate them from every vibration and force except one. Imagine a tiny, mirrored glass bead levitated by lasers in a perfect vacuum. In this state of extreme isolation, even the faintest nudge from a passing graviton could, in theory, cause a detectable shake. The challenge has always been that such a signal is immeasurably smaller than the quantum jitter of the bead itself. But now we are learning to squeeze light and matter, manipulating their quantum uncertainties to create a new kind of quiet. In this engineered silence, the whisper of a graviton might finally rise above the background hush of the universe. Alongside these sensors, our computational power is exploding. The equations of quantum gravity are so complex they have been effectively unsolvable. But with quantum computers, we can simulate these fundamental interactions in entirely new ways, modeling how gravitons might behave and revealing the precise experimental signatures we should be hunting for. This powerful combination of smarter machines and ultra-sensitive detectors is lowering the barrier to discovery, transforming the graviton from a philosophical concept into a tangible scientific target. So what would that first direct evidence actually look like? One compelling possibility lies in the data streams from gravitational wave observatories. As our detectors become more sensitive, we might find deviations in the waves from colliding black holes that cannot be explained by classical gravity alone. A specific high-frequency ringing in the waveform, for instance, could be the unique fingerprint of individual gravitons being emitted in the final, violent moments of the merger. It would be like listening to a bell and for the first time being able to distinguish the collective clang from the individual vibrations of the metal itself. At particle colliders, the search continues for that single, dramatic event where energy vanishes without a trace. But future colliders with energies many times greater than today's could produce a different kind of signature. We might not see the graviton itself, but we could observe its ghostly influence through rare particle decays. If certain particles begin to decay in ways that violate our current understanding of energy conservation, it could be a sign that they are briefly interacting with a graviton, a process that would open a door to the hidden dimensions of space. These are the subtle clues that could finally crack the case, turning a century of speculation into a moment of definitive proof. The horizon is no longer a mirage, but a landscape coming into focus, waiting for the first light of discovery to break. A discovery of this magnitude would shatter our world far beyond the laboratory. Holding the key to gravity itself means confronting a power that could rebuild civilization or tear it apart. The first and most chilling consideration is its weaponization. A gravity bomb would not explode with fire and shrapnel, but with a silent, crushing wave. It could increase local gravity to thousands of times Earth's normal pull, instantly flattening everything within its radius into a pancake of rubble. There would be no blast to shelter from, no radiation to contain, just an invisible, inescapable force turning structures to dust and living things to paste. Even more terrifying is the concept of a tectonic weapon. A precisely timed and placed gravitational pulse could trigger earthquakes, awaken dormant volcanoes, or generate tsunamis, using the planet's own geological fury as a weapon. The very ground beneath our feet would become a potential battlefield. Such power would create an arms race unlike any in history, a scramble for the ultimate deterrent that could make nuclear weapons seem primitive by comparison. The nation or entity that first masters the graviton would command a force of nature, holding a strategic advantage so absolute it could redraw the global map without firing a single bullet. This would plunge the world into a new kind of Cold War, one fought in secret laboratories over the fundamental fabric of reality. Beyond the battlefield, the societal disruption would be equally profound. The sudden advent of widespread anti-gravity technology would render entire industries obsolete overnight. What happens to the global aviation sector when anyone can purchase a vehicle that floats effortlessly? The entire logistics and shipping industry, built on trucks, trains, and container ships, would collapse. The value of real estate would be upended. A penthouse view loses its exclusivity when anyone can build a home in the sky. The economic foundations of our society, from transportation to construction to urban planning, would be washed away in a single technological tide. This is not merely an industrial upgrade, but a complete restructuring of human civilization. The potential for chaos is immense, demanding a global conversation that must begin now, long before the first graviton is ever confirmed. We cannot afford to wait for the discovery to force these questions upon us. The development of international frameworks and treaties, a kind of Geneva Convention for gravitational technology, is not a luxury but a necessity for our survival. We must establish clear, binding rules against tectonic weaponry and gravity-based arms. We need global agreements on airspace management for personal anti-gravity vehicles and protocols for the equitable sharing of the energy benefits. The graviton does not belong to a single corporation or nation. It is a secret of the universe. Its control must be a responsibility shared by all of humanity, guided by a moral compass strong enough to steer us away from destruction and toward a future where this awesome power uplifts everyone. The greatest challenge posed by the Gravitron may not be finding it, but proving we are wise enough to wield it. A growing and respected faction of physicists argues we are chasing a phantom. They propose that the graviton is not a fundamental particle, but a mathematical mirage, an artifact of our insistence on forcing gravity into the quantum box. The core of their argument is both simple and profound. Perhaps gravity is not a force like the others, and therefore does not need a messenger particle. Einstein's general relativity describes it as pure geometry, the dynamic curvature of spacetime itself. In this view, there is no force of gravity, only objects moving along the straightest possible paths in a warped landscape. The Earth orbits the Sun not because it is pulled by a force, but because the Sun's mass has created a valley in spacetime, and our planet is simply following the curve. To quantize this geometric effect, to chop it into discrete packets, might be as misguided as trying to find the particle of a hill or the quantum of a valley's slope. The geometry is the reality, smooth and continuous. The continued, profound failure to detect the graviton in any particle collider, despite decades of searching, is seen by skeptics not as a technical limitation, but as a crucial clue. It is evidence that we are looking in the wrong place because the thing we are looking for does not exist in the way we imagine. The universe may be telling us that gravity is a unique and fundamental feature of the cosmos, operating by a completely different set of rules than the other forces. This geometric perspective is elegant, but it faces its own monumental challenge. How does it account for the bizarre, probabilistic world of the quantum, where particles can be in two places at once? If spacetime is a smooth continuum, what happens when a massive object is in a quantum superposition? Its gravitational field would also have to be in two places simultaneously, a paradox that the smooth geometry of general relativity cannot easily accommodate. This is the stalemate that keeps the debate alive, a deep and unresolved tension at the heart of modern physics. Silent cities drift among the clouds, their spires gleaming in the perpetual sunlight, free from the anchor of any world below. This is the legacy of the Gravitron, a future where our understanding of gravity has rewritten the rules of human existence. The very ground becomes a choice, not a constraint. We would no longer be creatures of a single planet, but citizens of a solar system connected by gravitational conduits. A journey to Mars becomes as routine as a cross-continental flight, a matter of surfing the customized contours of spacetime between worlds. The concept of distance, which has defined exploration and isolation for all of history, simply melts away, but the transformation goes far deeper than transportation. With a complete understanding of gravity comes a true map of the cosmos, one that includes the invisible 85% governed by dark matter. We would perceive the full architecture of the universe, seeing not just the glittering stars, but the massive, hidden gravitational skeletons upon which they are hung. This knowledge would answer our oldest questions about the birth of the universe and its ultimate fate, granting us a cosmic context we have always lacked. Our place in the universe would shift from one of lonely speculation to one of informed belonging. We would understand the fundamental forces that birthed galaxies and life itself, recognizing the same principles that curve spacetime also pulse within our own atoms. This connection redefines human potential. The same curiosity that drove us to hunt for an invisible particle would have unlocked a stage so vast it challenges comprehension. We would become a species that molds spacetime, that communicates through gravity's whisper, and that draws power from the fabric of reality. The Gravitron is more than a particle. It is a promise, the key to our evolution from earth-bound inhabitants to conscious architects of a cosmic destiny. Our journey has taken us from the deepest abstractions of quantum theory to the soaring cities of a gravity-free future. We have traced the path of a single hypothetical particle, the graviton, and explored how its discovery could unlock the Gravitron, a power that reshapes our very existence. The challenges remain monumental, a maze of mathematical impossibilities and experimental silence that has tested the greatest minds for a century. Yet the potential is so thrilling it borders on the transcendent. This quest is far more than an academic exercise. It is the human spirit reaching for the final piece of a cosmic puzzle. Our reality stands on the brink of a revolution, waiting for one crucial insight to tip the scales. The next great discovery in physics could be just around the corner, hidden in the quiet hum of a quantum sensor or the faint ripple from a dying star. All it takes is one moment of clarity to change everything. Stay curious, for the universe is still whispering its secrets, and we are finally learning how to listen.